Cool. All right. So last time we had essentially finished up what we needed to talk about for the moment about oxidation and reduction of alcohols, at least to ketones and aldehydes. And what we wanted to do at the moment, or where we wanted to go next with this, is just kind of pick up a little bit of something that we skipped over in the first semester. Not that we couldn't have done it there, not that you guys already don't know the answers, but it's just kind of, I don't know, I think it's kind of something that fits in here a little bit better, sort of. And the book comes back to it at this point anyway, so I don't know why they introduce it the way they do, but originally in chapter 8 is where they started talking about some of these reactions. And then they're like, hey, we'll come back to it later. And then they do in chapter 13. Put it all together. I don't get it. But anyway, so how does this relate, I guess, to what we're going to be doing? I really don't know. I'll think of something clever by the end of this, by the end of the class, I guess. I mean, it does involve an oxidation and all these kind of things, but it's not quite the same way that we had before. But the utility of what we're going to learn is how we can start to add more than one functional group, or how we can start to add bits and pieces together to add different functional groups. I guess would be a good way to think about it in that way. So, learning a little bit about a somewhat unstudied, at least for our sake, functional group. And that is these guys here. Okie dokie. Okay. So we got an oxygen and we got 2 carbons on either side of it. Right, so on the surface level, we would say that's an ether, right? This is a fair assessment to make, right? But when we have an ether in a 3-membered ring, that's what's called an epoxide, right? So an epoxide. Now, much like the prophets of old, I told you guys in Ochem 1 that I would come and ask you a question in Ochem 2. Right? So I think today's the day that the prophecy comes true. As it was written, all right. So, but anyway, so I'm going to ask you a question, and when I told you guys that you already know the answer to this stuff, okay? I'm not going to teach you guys anything new today. You guys aren't men. Okay, that means 2 things. You're like, well, I'm happy that I know chemistry without having seen it before. I'm glad that I can participate and understand in class, right? Which is really the goal of these things, right? Because as I've always told you, we have a we have a textbook there that has, 24-ish chapters or so in there. How much of organic chemistry does that cover? Right, a little bit, okay? Right? The goal is when you guys are all out in graduate school pursuing chemistry degrees, that you guys will be able to draw back on these initial ideas here and then be able to come up with your own science, right? Because I can't teach you all of organic chemistry. I don't know it, right? I barely know this stuff. I just make it up as I go along, huh? Do you guys ever think about that? There you go. He says positive and negative a lot. Sounds good to me. Nobody's looked up if I actually have my degree or not. He's got a nice shirt that he talks fast. All right, he's a professor. So, anyway, but the point being is I'm going to have you guys think about this. I want you guys to come up with the answers for it first, okay? So I want you guys to see what happens, okay? When I take an epoxide, right? We'll keep it simple, right? The simplest of simple here. Okay, so I've got an epoxide. Good. We're going to do something drastic with it. Okay. And we'll see what you guys can come up with as an answer. want you to think back about what you learned in Gen Chem 1. Gen Chem 1. Wow, that always comes important, but what you learned in Organic Chemistry 1. Okay? You're allowed to use your previous notes. I'm kidding. I just know it all. Jeez. You're not allowed to use the book, right? Don't worry, Dr. H. I don't do that. So it happens all at once. Why are you saying that? So give me a reason why you can't, based on what you have. Where would this come from? This could only come from after that happens. You get what I mean? So do that first, and then do that. Right? Not too far off, but think about this here a little bit. Right? Think about that a little bit. So you got arrows, you got the McDonald's arches, right? You got arrows that are pointing in opposite directions. Right? Remember, arrows always go head to tail, head to tail. What is this? What's the point of it? What's the purpose of an acid? Okay, do you have it? Where's the proton going? Right? So if you have an acid, use its acidic character in the first step. Right? So same question here. What is this? Right? So use that in the first step. Yeah, I'm going to Blackwood. How's that animal feeling? Okay, so what's your grab at something? Where's your head? There you go. Okay, be careful. You missed something very, very important. That's good. That's what happens. You missed something very important. So think about what you did. Okay, so I like that, right? That'll happen. But think about why that can't happen. You almost got the steps there, folks. Okay, make a bond. Good. Good, okay. Interesting. It's not a bad thought. Good. just finish class in the next 10 minutes then, right? I just have to keep making stuff up. We talked about epoxides, and these are epoxides. Okay, all right. So, all right. We have an acid. It's going to act like an acid, right? We have an oxygen-containing functional group. Okay, pretty much any oxygen-containing functional group is going to have a partial negative around that oxygen. Right? We've seen this with alcohols, and here we start to see a little bit with these ethers. Okay, so we end up making an acid act like an acid. I know. I was stunned when I learned this also. Right? We've seen this happen over and over and over and over and over again, right? Remember, this is one of these things that I always try to impress upon you guys, right? When you have an acid, it almost always is used in the first step, okay? Now, do you guys catch what I mean with this? If I'm saying use the acid in the first step, what's the purpose of an acid? Acids are proton donors, so make the proton do something, okay? You guys with me on this? Okay. What's the consequences of our actions here? So what we end up doing is this, right? Okay, somebody hit me with some knowledge. Okay, that's what we ended up doing. Okay, good. Correct, right? Anytime we see a formal charge of a positive on the oxygen, we got to take care of that, right? What else?
The ring strain.
Okay, the ring strain, what does that mean? Take care of the ring strain would be good. What else? Aha, we'll have to take care of the bromide. That'll be useful. That'll come in the next step here. What's the mechanisms that you guys learned in the first semester? I can't do resonance structure. The what mechanism?
Sumo.
Oh, interesting. What's a Sumo mechanism? What's some of the characteristics of a Sumo mechanism?
Temporary protection or temporary partial carbocation.
Kind of. You guys remember what a Sumo is? Yes. What's a Sumo mechanism then? What are the intermediates that we see? Maybe it's in your notes. I'll give you a hint.
Do you mean like the three-membered ring?
So every Sumo mechanism had a three-membered ring, right? What else was part of that ring? Something very, very important. That ring always had what kind of charge? A full positive on one of the atoms, right? You guys remember this? So what do we have set up right here? A Sumo mechanism. There's no difference to it. Got it? So what else do we remember then about our Sumo mechanisms? How did they behave?
They lean to one side, causing.
That's right. So the central atom, the thing with the positive charge, starts to lean from one side to the other, right? Don't make me do the dance again. I gotta retain some dignity, right? Right? Remember, it starts to pull from one side to the other, and it leaves a partial positive behind. Got it? So what do you think is going to happen here? The exact same thing. You guys with me on this? Okay. Where is it going to leave behind the partial positive? On the most substituted side. In this case, they're both equal, right? Got it? You guys with me on this? So what's my product going to look like then? Well, remember what we're saying here is that when we set up a Sumo, right, where we have that three-membered ring and the positive charge in the middle, right? We take a look at the two atoms involved in the ring, or excuse me, the two carbons involved in the ring there, okay? And we have to identify which is the most substituted, and we leave behind the partial positive, right? And then we bring in our nucleophile. Okay? Our nucleophile does what? It comes in from what? The opposite face of where that positively charged atom is. Right? Remember we talked about sterics. That oxygen, whatever that positive thing is at the top of the ring there, that's blocking the nucleophile from coming in from that side. So the bromine adds from the opposite face of wherever that oxygen is, or whatever atom is part of your Sumo mechanism there. Got it? Why? Why does this mechanism work this way? Why does that oxygen atom start to try to pull at one of the two carbons? This is important. I think you mentioned it.
That oxygen doesn't act in one of the two bonds.
Right. Right? So why does it start to pull at one of its two carbons? What's it trying to do? Break one of those bonds, right? Try to get rid of that partial positive charge. But if it completely breaks that bond, what does it leave behind? A positive on a carbon, also known as a carbocation, right? Is it easy to form carbocations? No, right? Could you form a carbocation here? Probably eventually, right? Maybe you could, right? But it's much easier, right? Let's say lower energy for it to kind of just try to lift up one of its legs or the other, right? So remember that the second step there, we have a nucleophile coming in on the opposite side of a leaving group is what it essentially is. You with me on this? So what does that describe? Nucleophile attacking on the opposite side of the leaving group. That's SN2, right? Remember when we talked about these Sumo mechanisms, we said they're a combination of SN1 and SN2. We attack the more substituted carbon, which is SN1 like, right? Because of which way it's doing its dance. And then the nucleophile comes in from the opposite side, which is kind of like an SN2. Good? So why does it do the dance? Well, because we have to relieve that positive charge on that central oxygen, or whatever that central atom might be. Make sense? So I'm going to ask you guys another question. Okay? So we got this thing called an epoxide, which is a three-membered ring with an oxygen in it. Okay? Okay? So see what you guys come up with. Boy, hopes and dreams. All right, here we go. Something new we haven't seen before, huh? Okay, so let's use the most powerful tool we can. The false COVID positive test. No, I'm sorry, Dr. A is going to go quarantine, all right? No. What's the most important thing we can always do? Stop, right? Think, and then try. No. And always take a look at what we're doing, right? So what do we have here? We've got an epoxide. Now, what's one of the most important things to recognize about an epoxide by itself? It's a three-membered ring, okay? There's always going to be ring strain. What do you guys remember about ring strain from the first semester of OChem? Talked a little bit, and we did a couple examples about ring expansions, right? Why did ring expansions happen? To get rid of ring strain. You guys get what I'm saying with this? Would it be a good thing to get rid of that ring strain there? Yeah. Okay. What's the next thing that we notice? We're under basic conditions. Why is that very important to recognize? It can go after acidic hydrogens. Don't have too many acidic hydrogens here, to be honest, right? Got a bunch of alkyl hydrogens. Need a very good reason to go after those. Well, what is under... That's another way of asking the same question, I guess. What do we know about intermediates under basic conditions? They'll usually have what charge? Negative, right? So it's not a bad thing to make another negative if you're under basic conditions, right? That's a fair thing to do, right? But you better not be making any positives unless there's a very good reason to do that, okay? Later on this semester we'll learn a mechanism where we end up seeing a positive, I think we'll learn it. Yeah, there's like one mechanism I think we'll learn where we'll see a positive end up under basic conditions. But it's pretty rare. There's a darn good reason why it happens. Okay, what else do we notice? We're under basic condition, there's ring strain, it's an epoxide, there's no overtly acidic hydrogens, right? We have a good nucleophile. You guys catch the important difference here? We said there's no overtly acidic hydrogens. What does that mean? What are the fastest reactions to happen? Acid-base reactions. Got it? If we can't do acid-base, what's going to happen next? Nucleophile, electrophile, right? You guys catch this? If you can't do acid-base, do a nucleophilic attack. AKA, find your negative and find your positive, right? There's a theme that's going on in this class. Do you guys catch it? It's very simple. It's find your negative and then find your positive, right? Now I get, right, the trick is, where's the negative, where's the positive, that kind of thing. But you guys know exactly where your negative is. It's on that oxygen. Got it? Where's your positive? On one of the carbons in the epoxide ring there, right? Okay. You guys got it? So what happens? Sumo mechanism, we have a positive, the central atom in the three-membered ring has a positive charge on it, right? So we don't have that here. That is an important distinction. I'll tell you guys why in just a minute, right?
So it would be like a dipole positive?
Yeah, we just have a partial positive because of the difference in electronegativity, right? Those carbons in the ring there are feeling partially positive. Do we have a really strong negative? Yeah. Okay, so what happens? There you go. Negative attacks the positive. So hit the carbons. Okay. Yep.
When the nucleophile attacks, because would it also attack on the opposite side of the oxygen?
That was the exact question I was about to ask, right? You'll notice that the incoming nucleophile attacks on the opposite face of where the ring is open. Okay, why? Well, one side of this face, one face here is still blocked, right? That oxygen is still on one side, so whatever comes in has to come in from the opposite. Why in the world would this happen? What did we gain and what did we lose by doing this? Okay? What's something good that happened? We got rid of the ring strain, right? That's something good. What's something bad that happened? Well, take a look, right? In the starting material, we've got two carbon-oxygen bonds, right? I'm talking about these here, right? You guys with me on that? We've got two carbon-oxygen bonds. At the end, we've got two carbon-oxygen bonds. Remember, carbon and oxygen, very good friends. Makes very strong bonds, okay? So we made a sigma bond, and we broke a sigma bond. So there's no net gain or loss there, at least. That's kind of useful to recognize. Where did our negative charge start out? On an oxygen. Where's the negative charge now? On the oxygen. Does that make sense? Is that a fair trade? Yeah, it's basically a toss-up there, right? You start on an O with a minus, and you end up with an O with a minus, right? So what's driving this reaction to happen? Well, it's got to do with the ring strain is what it is. We're not putting the negative on a better place. We're not making stronger bonds, right? We're just relieving the ring strain there. Okay? Does that make sense? What do you guys think you have to do to finish this up? Now we've got an O with a minus charge. Let's turn it into something useful. Yeah, do an acid workup in there, right? So you can finish it up with an acid workup, and then you'll end up with an alcohol and an ether coming off of this, coming off the same molecule there. So typically what you would end up doing then, right, in the second step is just do an acid workup, where you see it like that, or H3O+, right? And we end up protein or alcohol. Good? How's this different from what we saw before? Well, before we set up a Sumo type mechanism. Got it? This is important. These aren't the same mechanisms. One follows a Sumo type, the other follows essentially an SN2, right? We attack on the opposite side that something's opening up, right? You guys catch that very important difference. So I'm about to ask you a question. Okay? Ready? Let's keep it simple. Tell me what the product is. And tell me what the product is. arrows pointing in opposite directions. Arrows always chase each other, head to tail, head to tail, head to tail. Be careful, right? What's this mechanism look like? So we have an incoming nucleophile hitting on the opposite side of the lead group, right? So it's more like an SN2. And what we know is one of these key ideas of an SN2 reaction. Begins with an S, which is what?
Substitution.
Okay, you got me on that one, right? Another very important S. What do you mean? No, that's not the issue. That's not the issue. Why that? Why? What difference does it make what type of mechanism is this racing? What's the key part? The key part of SN2. Okay. That's the question. Why are those carbons feeling? Why are these carbons feeling positive? What's it for? So is there a difference between the two? No, there's not. Right, it's both pulling on both of those, right? So which one's going to be feeling positive? Both. Which one feels more positive? Neither. Got it? So both are equally. Yep. What type of mechanism is this? Basically, what's the other? What's the key part of SN2? You got it. There's some music playing, right? Looks like the opera followed us over here this semester too. That's great. Fantastic. I do miss it. It's really classed up the joint, you know what I mean? So under acidic conditions, right, that's our product there. Okay? What does that mean? Means under acidic conditions, our incoming nucleophile, whatever we add, that gets added to the more substituted side. Why? What mechanism is at play? Or at play is the Sumo mechanism. Got it? And there we end up making these partial carbocations, right? They don't shift, they don't rearrange. We end up making a partial positive on the more substituted carbon, and so the incoming nucleophile is going to attack that carbon there. Got it? Is it a full carbocation? No. So if you draw a full carbocation on the exam, what happens? Yeah, no, that's okay. Well, you guys asked for it. All right. I was just going to say partial credit, but you guys are like, no, just go ahead and fail me. At this point, just go ahead, we're done. All right, but you guys get the point? So partial positive, not a full carbocation. Okay. What about the second one there? So here's the important difference, right? The black or the pink carbon, which one's feeling more positive? Neither. Got it? Why are those carbons feeling positive to begin with? No Sumo mechanism. That's the important difference. When does a Sumo set up? Three-membered ring and a positive atom as part of that three-membered ring. Got it? So we don't have a Sumo mechanism going on down here. Why are those carbons feeling positive?
Because of the electronegativity.
Because of electronegativity, right? So what's electronegativity? The oxygen's pulling on the bond to both of those carbons. Which one does it pull on more? Neither, right? It's about the same, okay? Put a little asterisk on that, right? Okay. But for our purposes, neither one of those is any more or less positive. Got it? So then, if we just follow that logic, then we would say, okay, so the black or the pink gets hit 50% of the time equally, right? We attack both of those equally. Well, what else is at play? You guys just made an electronic argument. You just said that both of those carbons are feeling equally positive. There's your electronic argument. What's the other good argument you always have to make? Sterics. You guys got it? Are these different sterically? Absolutely. Right? So which one's easier to hit from steric? The less substituted side. So guess what's going to happen here? Attack of the nucleophile on the less substituted carbon. Got it? Alright, so we would do something like this, where we finish up with an acid workup, right? So, the bond in black. Why do I change colors so much? That looks great. All right. Cool. Got it? Sound good? Your poor eraser. I'm sorry. It's okay. Does this make sense? Do you guys see the very important difference between when you're under acidic versus basic conditions? You add to the more substituted side, you add to the less substituted side. That's important to recognize, right? That gives us some method of selectivity between the two different carbons that are part of this epoxide. Got it? Cool. Who cares, right? Well, let's see. Let me think here for just a second. Let me see how I can challenge you guys this afternoon. I'm used to a morning class, sorry. Well, we'll make it easy for now. All right. Okay. my pen anywhere. My life's just filled with problems. What in the world is part 1 there? What do we got?
Ionic compound.
It's one of our organolithiums, right? Now, what do we know about our organolithiums?
Strong base.
Extremely powerful bases, right? Extremely powerful bases. So we always have to be on the lookout for what? Not just something positive, but if we're a really powerful base, keep an eye out for acidic hydrogens, right? Because that'll be instantly what happens. As soon as you have an acidic hydrogen near one of those things, they're going to come together, right? Fortunately, we don't have to worry about that here, right? No acidic hydrogens. Powerful bases, which also makes them. Yeah, we have, so just as a quick aside here, they're really not all that great at being nucleophiles, but they're okay-ish, right? Just because they're such powerful bases is what the distinction is. We will see some cases later on where these will be acting far more basic than I'm kind of letting on at the moment. So just understand that when we're saying these are really basic, they are really basic. Right? The only time they're going to act as a nucleophile is if there's really nothing else for it to go after. Okay? Now we can modulate that, and we'll learn a little bit more about that later. We'll kind of rein back its basicity by doing something to them. So we'll see these things come up again, but for the moment we can kind of consider them okay-ish nucleophiles. Right? What's up?
Question, how many carbons are in that chain?
Great question. How many carbons are there? 4. Okay, this is one of these key things to pay attention to when you're dealing with these Grignards and your organolithiums. Okay, count your carbons. Number them is what I tend to do, right? Or in here, when I'm working through with you guys, I put colored dots on each one of those, right? So that they stand out. Okay, but that's something that's very easily missed. And what's my second favorite thing to do? You know, you're smiling. They missed a carbon, and time to take off points, right? No, but always keep an eye out when you guys are working with these organolithiums, right? Not to drop or add carbons.
So, this example, when you have the bromine reaction, does that make sense? Like how many carbons are?
Oh, maybe I added one here. But if that's what I drew for you guys, then I added one too many for you. Sure, that's right. Yeah. So sorry. No, there's no way I'm going to mistake. What are you talking about? So we got 4 carbons there, right? Powerful bases, good nucleophiles, an epoxide, right? So what's going to happen? Everyone act like you're really smart. They're putting this on display here, right? So don't look at the camera, right? Right? So what do we have then? We got an epoxide under strongly nucleophilic conditions. What's going to happen? Yeah, right. The nucleophile is going to attack, right? Which carbon is it going to attack? The less substituted side, right? So is this going to behave any differently than what we saw before? No, right? So remember, what I do here is as soon as I see an organolithium, I just kind of get rid of that, right? And I just put a negative charge there wherever that lithium or the magnesium bromide was, whatever that might be. Okay? Can you guys do that on an exam? Be careful. You put an extra carbon on yours. Yeah. No, that, like I'm saying, it's so easy to do. Yeah. So is it all right for you guys to do this on the exam? Okay, let's go with this. I keep asking you guys questions, and you guys always say, no, fail me, take off points. I'm like, oh, geez, these guys are so harsh on that stuff. My goodness. That's, and I'll joke aside, that's perfectly fine to do on the exam, okay? I don't see any issue with that. Cool. All right. So, okay. So bond in red to 4 carbons there, right? Cool. Why did this happen? Why would this reaction want to happen? Ring strain gets relieved, that's good. Why else?
The negative, the partial negatives on oxygen. So
Not the partial negative, the full negatives now on an oxygen. Do you guys catch why that's important? Where did the full negative start out? On a carbon. Is carbon good at handling a negative? No. Is oxygen way better? Yeah. So there you go. Good. And then the last step there, I would turn that into an alcohol. Got it? Nice. What's useful about this? Aha, right? So this is another example where we can make carbon-carbon bonds. Got it? So now we can make carbon-carbon bonds from our carbonyl groups, okay? Using our Grignards or lithiums. And now we can use epoxides to start to string things together. Will epoxides behave differently than aldehydes or ketones? Yes, they will, right? There's different reactivity, right? Have we talked about how ketones behave under acidic conditions? Kind of, right? Kind of we have. We'll talk about it a little bit more later. Right? But the point being this, remember one of these underlying tones that I'm always going to want you guys to think about is how do different functional groups react with under acidic conditions or basic conditions, right? With nucleophiles or electrophiles. What's the selectivity for different reagents? What's the selectivity for different functional groups? Got it? Epoxides are going to behave very differently than, okay, well I shouldn't oversell it, I should say. But epoxides are going to behave differently than aldehydes and ketones will, okay? But in some cases we can still see some similar reactivity there, okay? All right, oops, oh, that doesn't really matter. So I think you guys got the coloring at this point. Good? So what's your next question? So now we know how epoxides react under acidic conditions. Now we know how they react under basic conditions. So your next question should be, how do we make an epoxide, right? Okay, how do we make an epoxide? Well, we got 2 ways to do it. One that sucks and one that's okay. Have I sold you on it yet? Okay. So 2 ways to make an epoxide. All right? All right. 10 minutes. And it's a full day of me not listening to myself talk. Very sad. All right. Okay, so starting with an alkene. From an alkene, we can turn it into an epoxide, is what it is. What we will need, how does the book put it? I forget. I think they show you guys, I think they show it to you like this. Yeah. Okay, so that's a weird looking functional group. So it's a carbonyl with an oxygen bound to another oxygen. Okay, so real quick. So whenever you see an oxygen bound to another oxygen with a single bond, right, that's a peroxide, okay? That's a peroxide bond is what they call it. Now you guys already knew that, right? Because if I replace that carbonyl end with a hydrogen, we have H2O2, right? Which is a buddy hydrogen peroxide, okay? Now, what we have here is a peroxy acid, is what we would call this, a peroxy acid. So you guys see how that's a carboxylic acid, right? But basically an OH at the end of it, right? So peroxy acid is what we call this, okay? Now, whenever you see a peroxide, there's two things for you guys to start to think of. One, you can probably guess that it's going to do an oxidation, okay? In fact, I think that's a fair statement. Yeah, I might be missing one reaction, right? But on quick review, every peroxide that you've used so far has caused an oxidation to happen, okay? Now, your your hydroboration oxidation, right? Your BH3 with THF, right? Sodium hydroxide, hydrogen peroxide, right? You added an alcohol. That's an oxidation, right? When you were doing your anti-Markovnikov addition of a halogen, right? HBr in peroxides, right? You didn't add an OH, but you added a halogen. That's an oxidation too, okay? In the classical sense of oxidation, right? The reducing, excuse me, I gotta be very careful with my terminology here, lowering the oxidation number, right? Making it more positive, right? So every peroxide that you guys have used so far has caused an oxidation, so it's probably not a shocker here that this is going to cause an oxidation also, okay? The mechanism for this is in the book. It's kind of weird looking. It's applicable to this reaction. And remember that promise that I made for you guys there, that if it's a mechanism that's only for one reaction, I'm not going to expect you guys to know it, right? So, we're all good. Oops, I'm done. Let's try this one more time. So, at the end of the day, that's it, okay? Now, the book goes through when it talks about retention of stereochemistry and all that kind of stuff, and that's useful to recognize, okay? The technical product here, okay, would look like this. Okay. And okay. So if we started out with a trans alkene, right, we end up with a series of trans products there. And enantiomers and all that kind of stuff with it. It gets a little bit more complex, and we can change it and vary it and blah, 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 right? But for argument's sake, okay, just so you guys can think about it that way, the stereochemistry that we start out with is what we'll see at the end there, okay? Which shouldn't be too much of a shocker, right? Because we start out with an alkene. Alkenes are planar. Right, so whatever we're adding can come in from both sides equally. Right? It comes in from one side, we end up with a dash wedge. It comes in from the other, it ends up as the wedge dash. Right? Good. Cool. All right. So there's two common peroxy acids that get used. The first one being peroxy acetic acid, which is just the peroxy acid of acetic acid, as you guys probably figured out. Right? Like, whoa, Dr. H, you're going a mile a minute, right? Peroxy acetic acid is what? So that's peroxy acetic acid, right? There's a certain problem with this. One problem is its solubility, right? It's very soluble in things like water, but not overly soluble in some other solvents. And that's a problem, because guess what you need when you're doing an organic reaction? A solvent, right? So the most common method that we have of doing this is something called Mcpba. Okay? And Mcpba looks like this. Okay, that's Mcpba. I'll spew a name at you guys here in a second. So MCPBA stands for meta-chloroperoxybenzoic acid. Okay? Now, I don't need you guys to know that right now. Okay? But if you type in MCPBA, you can look that up too, right? But here's something that we'll learn later, right? Within the next chapter that we'll get into, probably, we're going to talk to you guys a little about ethers. So probably Friday-ish, we'll probably start to get into that. We'll start to talk about aromatics and benzenes, okay? And then we'll learn where we come up with that name there, right? What does the meta mean? What does the benzoic acid mean? But you guys know what the peroxy means, right? So meta-chloro, right? Peroxybenzoic acid. So we'll talk about where the meta are, and that's part of the systematic name that you guys will learn this semester. That is one of these very important naming parts, okay? But there it is. So why do we care about that? Why do we use that? Well, this is far more soluble in a lot of organic solvents. Okay? So what we end up using, MCPBA is used quite a lot. It's a very common organic reagent. It can make epoxides, but it can also do other oxidations. It can oxidize amines. That's some of these reactions that we can end up doing with it, and that's important. Because an oxidized amine is going to behave very differently than a regular amine, right? So it's kind of a protective group almost for it. Okay? Cool. Good? I think that's a good stopping point. We'll start next time talking about ethers, which are just kind of derivatives of epoxides. Okay? What's up? The MCPA. These are the two common. I said there's two common peroxy acids that we end up seeing. Yeah. For our purposes, they don't really do anything different. I just wanted to say that, the MCPBA is used because of solubility. Probably.